Welcome to the another session of irrigation and hydraulic structure subject. In the previous lecture we have discussed about earthquake pressure, wave pressure, wind pressure and other ice pressure also we have discussed. How to consider the pressures which are acting on a different pressures which are acting on a gravity dam. So as per IS recommendations, IS 6512 1984 recommendations. So what are the different recommendations that we have to follow in considering those forces which are acting on a gravity dam have seen in the last class. Now here we are moving on to next topic, that is causes or modes of failure of a gravity dam. What are the different causes or what are the different modes of failure of a concrete gravity dam we are going to discuss in today's class. So as you are seeing, right, there are four different forces, major forces or modes of failure which are causing the failure of a gravity dam. In that, first and important force is overturning of the dam. So what is overturning force and how this overturning force is causing the overturning of the dam, because of which the dam is going to overturn and the dam may not be stable. It may lead to the failure of the dam, overturning of the dam. Now the second important force is sliding of the dam. So if the foundation is soft and there is no cohesion or friction between the foundation as well as the bottom of the dam, then in that particular case there may be a chances of sliding on the soft soil. So how these sliding force we have to overcome and what are the precautions we need to consider, that we will see. And the next important force is compression or crushing. What is compression force or crushing force, which is going to affect the stability of the dam, which may cause the failure of the dam, that also we will see. And the last important one is tension. How the tension force is developed in the dam, whether it is developed at the upstream side or downstream side, whether these compression and tensile forces will develop at the toe or heel. So where they will develop and how to control them, let us see in the next slides. The second slide, now let us discuss about overturning. What is the meaning of overturning? Overturning is nothing but it is the force which is developed to rotate or overturn the dam from the base. So this happens when the horizontal force acting on the dam overcomes the vertical stress. Means the horizontal stress is greater than more than the vertical stress developed in the dam. As we all know, the concrete gravity dam is alone resisting the forces by own weight. So the own weight will be developed in the dam, so that is creating vertical stress. If this vertical stress is less than the horizontal force acting, then there may be a chance of overturning of the dam. Okay, so in this particular scenario we have to calculate. So here we need to consider certain factor of safety to overcome this overturning force. So what is the factor of safety that we will see here? So factor of safety against overturning is the ratio between righting moments to the overturning moments. So what is the meaning of righting moment here? Righting moment is nothing but it is the ability of the dam, ability of any structure to regain to its original altitude. Means if some force is acting on the body of the structure, then after the release of the force it may regain to its original position. So that is called as a righting moment. So what is the righting moment of the dam to the overturning moment, if this ratio is considered as a factor of safety? So the factor of safety against overturning is factor of safety is equal to summation of righting moment to the summation of overturning moment. So by taking this, considering this factor of safety, we can overcome the overturning force. Okay, now coming to the second force. So what is the second force? It is a sliding force. So why sliding force will act on the dam? It is the sliding will be stopped only if and only if we provide proper cohesion or friction between the soil and the foundation. Then only this is possible. There should not be any leaky joints, there should not be any fisheries, and it should have a cohesiveness. There should be cohesion between soil, foundation soil as well as the foundation, and also there must exist sufficient friction between the soil of the foundation as well as the foundation of the base foundation of the dam. Then only we can avoid this sliding of the dam. So here you can see the resistance against sliding is due to the friction and shear strength. So it completely depends on frictional forces between the dam base as well as the foundation soil, and as well as what is the shear strength of the soil. Okay. So if no shear strength is considered in the design, if no shear strength is considered, then what happens? The factor of safety is known as factor of safety against sliding. So then only it is considered as factor of safety against sliding if no shear strength is considered in the design. Okay. Suppose if shear strength is not considered in the design, then we are calling it as factor of safety against sliding, FSS. So how this FSS is calculated without shear strength? Then here the formula is given, that is mu by tan theta is equal to mu into summation of vertical forces divided by summation of horizontal forces. Here what is the meaning of this tan theta? Here tan theta is called as sliding factor. So here tan theta is called as sliding factor. So what is the meaning of sliding factor? It is the ratio between summation of horizontal forces and to the summation of vertical forces in the dam. Okay, so this is what will give you the tan theta values, and here mu is the, what is mu here? Mu is the static friction, which varies in between 0.65 to 0.75. So that value we can consider here. So the limiting values, so whatever the limiting or permissible values we can say, so they are given in the code 6512, 1972 and 1984. 1972 is the older version and 1984 is the revised version for this sliding force. Okay, so these permissible values are mentioned in the code book, in that code book. Okay, now moving on to the next slide here. For a low gravity dam, the sliding is resisted by the friction alone. Friction is sufficient to stop the sliding force in case of a low gravity dams. For example, in case of large dams, like large gravity dams, like very high gravity dams are there. So in that particular case, friction along with the shear is very, very essential. Both the things need to be considered in the design in order to overcome the sliding force in a large dams. Like heavy dams are there, heavy height, heavy material is there. So in that particular case, both friction as well as shear strength need to be considered in the design. Then only we can overcome the sliding force. Otherwise, it is not impossible. Friction cannot alone resist the sliding force in case of large dams. Okay. So according to IS 6512, 1984, what are the specifications given for factor of safety against sliding? Here you can see the equation is given as factor of safety against sliding is to be considered dependent on two factors. One is friction as well as the cohesion or shear. Friction as well as shear. These are the two things we need to consider in the design. This is as per the revised code, 1984 code. So older code is different, 1972 is different and this one is different. So here we need to consider the revised code only. So that is the code saying that we need to consider friction as well as cohesion or shear in the design, which needs to be included. So the revised formula is given here, that is F is equal to mu into summation of vertical forces divided by F5 plus CA divided by FC, okay, which equals to summation of mu into summation of vertical forces divided by F5 plus CB divided by FC divided by summation of horizontal forces. So here what we can see, mu is the static friction already discussed, summation of V is the summation of vertical forces, and Fi is this is frictional force, and CA, where C is the cohesion, and whereas this A indicates area of the dam, area of the joint, where we are actually considering area of the joint, and FC indicates the shear or cohesion force. So this is divided by summation H. So here A is nothing but B into 1, so B is substituted here, CB by FC. Okay, so this is the revised formula as per 1984 code. Okay, now moving on to the next slide. So these are the values of partial safety factors for FQ as well as FC. Sorry, F5 as well as FC. Friction force, friction factor of safety, as well as cohesion or shear factor of safety. So these are the values given. Friction factor of safety values as well as FC. Cohesion or shear factor of safety values are given. So both are partial safety factors. So these are considered for different load combinations, because it is very clear that as we are taking in case of RCC building design, we need to consider the load combination, because all the loads may not act simultaneously. So there should be a combination. So here also the combination of different forces. Till now whatever the forces acting on a gravity dam discussed, so they are considered as a combination. So for those combinations, these partial safety factors are considered, F5 as well as FC. So this is the tabular column given in the IS code, revised code 1984. Okay. Now next, third important force is compression, or which is also known as crushing. So these compression and crushing forces, how they are causing failure of the dam. See, material will be completely crushed or compressed. So in order to overcome this force, so we need to understand what is the normal distribution of stress at the base of the dam. So here the symbolic picture is given here. So here in the picture you can see the base of the dam is considered, the base width is small b, and exactly the center is marked at a distance of b by 2. Now at the center, let us assume the vertical force is acting and horizontal forces are acting in their direction. Let H be the horizontal force and capital V be the vertical force. So the resultant of these forces is considered as R here, and this R is acting at a distance of eccentricity E from the center of the base of the dam. So it is mentioned in the figure here, E is equal to sum from the base at a distance B by exactly from the center E. So at that location, E, resultant force of vertical and horizontal forces, is acting here. So for this condition, let us see now the distribution of stress, normal stress at any point on the base will be sum of the direct stress and bending stress. So it is the summation of both the stresses, direct stress as well as bending stress at the base. So what is direct stress here? Direct stress is V divided by B into 1, where 1 is considered as unit distance. So V by B, and if in case of bending stress, so that is given as M into Y divided by I. So if we substitute M, which is the vertical force, and E, if we substitute here VE by 1 by 6 into B square. So after simplification, the normal stress, so whatever the normal stress which is indicated with Pn, so that is considered as V by B into 1 plus or minus 6E by B. So this is the final equation for normal stress, right, Pn. So here plus or minus is considered because at toe we will get the positive value here, 1 plus 6E by B, and at heel we get negative here, 1 minus 6E by B. So at toe we can say that, at toe we can say that this is positive, so we will get compressive stresses, and at heel we will get negative stresses, so we will get at heel we will get what we call it as tension stresses. So positive indicates compression forces and as well as negative indicates tensile forces. Now let us move on to the further. Now here you can see, in the picture you can see the stress distribution below the base is considered here. The stress distribution here you can see. The following figure shows the stress distribution. So at toe, as we are telling that the toe is at toe, the stresses should be greater than the allowable compressive stress. So whatever the stress which is existing at the toe will be less than compressive strength in the foundation of the material. So here you can see B by B into 1 plus 6E by B should be less than or equal to allowable compressive strength F. Then only this particular base of the dam is safe against crushing or compressive forces. Otherwise it is not safe. Okay. So if E is, in case if E is B by 6, then what happens? This equation will turn into Pn at toe. Pn at toe is equal to 2V by B. So Pn at toe is equal to 2V by E, because 1 by 6 if we substitute here, B by 6 if we substitute here, BB will get cancelled, 6 will get cancelled, and it will remain only 2V by B. Okay. So this is the condition. It should be less than. In order to overcome compressive strength, eccentricity should be less than B by 6 only. If it is greater than B by 6, there will be a development of tensile forces. As concrete is weak in tension, it cannot resist the tensile forces. So that is, it is very, very important to maintain eccentricity E is equal to B by 6, less than or equal to B by 6 only. Otherwise the dam will be subjected to tensile forces and there may be a chance of failure of the dam. Okay. Now next slide, the tension. Final force is tensile force. How tensile force is developed? So as we have discussed at heel, which we are considering it as at heel, there is a development of the what we call tensile forces, which is Pn heel, that is V by B into 1 minus 6E by B. Suppose, as we have discussed, if E is greater than B by 6, the normal stress at the heel will be negative or tensile. So as I told you, the concrete is weak in tension. In order to overcome this tensile force, so E should be less than or equal to B by 6 only. That is the only thing we need to consider in order to overcome tensile force. For no tension, it should be less than. E should be less than or equal to B by 6. Okay. So these are the causes of failure or modes of failure of a concrete cavity dam. In the next class, we are going to discuss about profile of a dam, practical profile, or what is the elementary profile of a gravity dam. We will see.